Now the important question is that how is it useful to us, right? So in what way are we going to use it? Yes. Okay, we are coming to that. Okay, so we will discuss all those things, right? So in a certain sense, yes, of course, one can also argue the other way. Okay, that's why I'm coming to this one, right? So that's where I am going to say application of mapping theorem to stability analysis. Okay, that's what we are going to do. All right. So so application of mapping theorem. To stability analysis. Okay, so that's what we are going to do. So now, how is it essentially applied? Let's look at that question, right? So the way it is applied is the following. Okay. Now we will go back to our closed loop transfer function, right, and the closed loop characteristic polynomial, right, which is 1 plus g of s h of s, correct? So consider f of s to be equal to 1 plus g of s h of s, which was some do of s plus no of s divided by do of s, right? So that's what we already had, right? Now the question is that, like, how do I apply the mapping theorem to this polynomial, which is a ratio of two different polynomials, right? We are interested in the open loop, closed loop poles, right, their location. Okay. Now for closed loop stability, what is it that we want? Which poles? Closed loop poles, right? If I want my closed loop system to be stable, I want all the closed loop poles to be in the left of complex plane. That means that I do not want any closed loop pole to be either on the imaginary axis or the right half plane. Okay. So consequently, we will see whether we can use that to our advantage. Okay. So let us take the S plane. Suppose, of course, this is the left of plane, this is the right of plane. Suppose, let us say I take a contour where I start from the origin, I go along the imaginary axis, okay, to infinity along the imaginary axis, that sweep the entire right of complex plane, okay, like an arc in the form of a semicircle of infinite radius, and then come back to the origin. Okay. Suppose, let us say I consider such a contour in the S plane. So my contour, the closed contour in the S plane is a semicircle of infinite radius that essentially covers the entire right of complex plane. Okay. So first let us discuss it, then we will first let me convey the concept, then we will discuss any questions, right. So let us say this is the contour we are considering in the S plane. Okay. So let the closed contour, of course one can ask, okay, look, is this contour really closed? So would you say that, okay, look, you know, like when you take a arc of infinite radius, right, would you consider it to be really closed or open or something, right? So we will not get into that level of debate here, right. So we will say that, look, let the contour in the S plane, okay, be a semicircle of infinite radius that sweeps the entire right half plane. Okay, so that's the closed contour in the S plane. Okay, now we want essentially no closed loop poles within this contour. Do you agree? See, for closed loop stability, we do not want any closed loop poles to lie within this contour, right? That's what we want, right? We don't want any closed loop poles on the imaginary axis, neither do we want any closed loop pole in the right of complex plane, right? So, and if we assume that, as a first step, we assume that none of the open loop poles and open loop zeros lie on the j omega axis to begin with. Okay, then we will see, I will leave you with a question, what happens if it does not happen, right. So, see, I can have open loop poles and open loop zeros in the right of complex plane, that is allowed, right, but I assume that, look, for the open loop poles and open loop zeros, right, none of them lie in the right, on the imaginary axis or the j omega axis. Okay, so that is an assumption that we are what to say essentially looking at, right. Now, further we assume that limit s tending to infinity, see, this is what I would have typed here, let me go back to the handout so that I can explicitly point out which point I am essentially referring to. Okay, so these are the assumptions that we are looking at. Okay, so I'm going to write down this assumption. Okay, so limit s tending to infinity, g of s h of s is either 0 or a non-zero constant. Okay, so that's what we are looking at. So essentially we have limit s tending to infinity, g of s h of s is either 0 or a non-zero constant. Okay, okay, which is essentially saying that the system is causal. Okay, we have a proper transfer function to begin with. That's the class of system anyway we are dealing with. Why am I looking at this? Because then this will imply that when I am going on a circle of infinite radius, s is tending to infinity, right, is it not? Then that means that at that value of s, all the points will be mapped to one point in the g of s h of s plane. Okay, so that is the implication, okay, of the system being causal, right. Okay, so that these are some assumptions, okay, that we do. Now, this mapping, okay, is now this contour is now mapped into a corresponding contour in the 1 plus g of s h of s plane. Okay, so let us say, like I map this contour in the f of s plane, but what is the f of s plane? This f of s plane for stability analysis, f of s was 1 plus g of s h of s, right. Okay, so let us say, like that gets mapped into some arbitrary contour in the f of s plane. Okay, now recall that NC should be equal to z plus p, sorry, z minus p. Okay, so once again, what is z? Z is the number of zeros of f of s within the contour in the s plane, right. Now, for closed loop stability, we want z to be 0, z to be 0. Please remember, that is why let me repeat it again and again, right. Yeah, we need to just reflect on this a little bit. okay. So f of s was 1 plus g of s h of s. The zeros of this f of s, right, are the closed loop poles. We do not want any closed loop pole in this contour, all right. So that's why we want z to be 0. So what should be then NC? NC should be minus P. What is P? P is the number of open loop poles, right, which lie within this contour in the S plane, right. So you know the location of open loop poles. Anyway, we are given an open loop transfer function. We know where are the open loop poles within this contour, and I know the value of P, right. But of course, there is an important assumption, right. So that's where this assumption comes, right. We assume that none of the open loop poles and zeros lie on the j omega axis, because the original mapping theorem states that you consider a contour where none of the contour does not go on, pass through any of the poles and zeros of that function f of s, right. That's an assumption that we are doing. We'll then see what happens when we see. Sometimes we may be given, you know, like open loop transfer functions where there are open loop poles on the imaginary axis. Can happen. Let's say you take a PI controller, you will have a pole at the origin, right. We have already seen it. Then can I choose this contour? We'll ask ourselves that question later. For the time being, we'll first deal with the initial simpler case where there are no open loop poles on this j omega axis, all right. So that's what we are. So now what does this say? So this essentially tells that for closed loop stability, okay, the contour in the 1 plus g of s h of s plane should encircle the origin P times in the counterclockwise direction. Do you agree? That's what is required for stability. Okay? Right? We are not done yet. We are only halfway through. Right? Do you agree? Okay? So that's what this equation tells me. Right? Now I am going to essentially go from this 1 plus g of s h of s plane to the g of s h of s plane. So please note, you know, like we are talking about closed loop stability. So what it means is that for closed loop stability, the contour in the 1 plus g of s h of s plane should encircle the origin P times in the counterclockwise direction. That is a condition. If it does not, the closed loop system is unstable. Okay, that's what we can conclude, right? Yeah. So now from the 1 plus g of s h of s plane, we go to the g of s h of s plane. Now how do I draw a contour from the 1 plus g of s h of s plane to the g of s of s plane? I subtract 1. See, how do I get g of s h of s from 1 plus g of s h of s? Minus 1, right? 1 plus g of s h of s, you can immediately see that 1 plus g of s h of s minus 1 is going to be equal to g of s h of s. So, see, of course, this is very simple. Why am I writing it? Essentially what it means is that the contour in the 1 plus g of s h of s plane is shifted to the left by 1 unit along as far as the real part is concerned. So you take all the points in the 1 plus g of s h of s contour, you just shift the real part of all the points by 1 to the left. That means you are subtracting 1, then you will get the corresponding contour in the 1 plus g of s h of s plane. Let us say that contour is something this, okay, similar shape, okay, but that's something like this. Okay. Now where is the origin shifted? See, let us say this is my origin, which is the critical point, right, as far as the mapping theorem is concerned. What is this critical point shifted to? So the origin of the 1 plus g of s h of s plane is shifted to You are subtracting 1, right? What is 0 minus 1? Minus 1, right? So it is shifted to minus 1 in the g of s h of s plane. Okay. So we can say that the number of encirclements of the origin in the 1 plus g of s h of s plane is the same as the number of encirclements of the origin of the minus 1 point in the g of s h of s plane. Do you agree? So let me repeat that statement once again. The number of encirclements of the origin in the 1 plus g of s h of s plane is the same as the number of encirclements of the minus 1 point in the g of s h of s plane. I have not changed the function, I have just shifted the contour by 1 to the left, alright? Yeah. P is, if P is a non-zero number, then that means the open loop system is unstable. See, P indicates open loop poles, right, within the contour. Yeah, you can have an unstable open loop system. Question is that by feedback or you stabilize it, right? That's what you are asking. You can have, right? Okay. So I hope how the critical point becomes minus 1 in the g of s h of s plane. So the same condition, one can rewrite this as the contour, that is for closed loop stability, the contour in the g of s h of s plane should encircle the origin p times, sorry, should encircle the minus 1 point, not origin, okay, minus 1 point p times in the counterclockwise direction. Okay, this becomes the Nyquist stability criteria now. Okay, so we are not done yet, you know, like we are just going step by step. Okay, this is a penultimate step. Okay, then we go. I hope it's clear, right? So because whatever is the number of encirclements of the contour in the 1 plus g of s plane, when you map it to g of s h of s plane, it will be the same as the number of encirclements of the minus 1 point, because you are just subtracting 1. That's it. You are just shifting everything to the left by 1. Right? So the critical point, which is the origin in the 1 plus g of s h of s plane, becomes the minus 1 point in the g of s h of s plane. Right? Is it clear? Now you are seeing that this contour in the S plane is also like very, very special. It's not an arbitrary contour, right? Like the general example of the mapping theorem that we looked at. So if you look at the S plane, what is the contour that we are considering? It is a semicircle of infinite radius that goes from minus j infinity to plus j infinity, then sweeps the entire right of plane and then comes back. Alright, so this is like infinite radius, right? LHP and RHP. Okay, so this is a semicircle of infinite radius that sweeps the entire right of complex plane. Is it not? Okay. Now the question that arises is that what sort of form that S takes in this contour. So note that S is of the form j omega, right? Omega belonging to minus infinity to plus infinity, right? In this contour. Is it not? Anyway, when S sweeps in the arc of infinite radius, g of s h of s is a finite number. It's going to be the same point. That's our assumption from that's the consequence of causality, right? We are assuming that the system is causal. So as a result, when I go on the arc of infinite radius, g of s h of s will be at a point. That's it, right? It's not going to vary. The variation is going to come only in the part where S goes from minus j infinity to plus j infinity. In that region, in that contour, S is purely imaginary. Is it not? So this implies that we are going to be interested in the plot of, rather than saying g of s h of s, because S is of the form j omega, we are going to be interested in the plot of g of omega h of j omega as omega varies from minus infinity to plus infinity, right? And what is this plot called as? The Nyquist plot of the open loop transfer function, right? If you give me any transfer function, you substitute S equals j omega and see how omega varies from 0 to infinity, that is the Nyquist plot. Of course, here we are treating omega as a parameter, so I am making omega to be negative also, and I asked you a question last class, right? What happens when omega becomes negative, right? We figured out that in a certain sense it becomes a mirror image, right, about the origin, right? So essentially that is what is going to happen here. So that is why we are essentially going to be interested in the Nyquist plot of the open loop transfer function to figure out the closed loop stability. So that is what leads to the statement, okay. So let me go back, we will read this statement and we will come back and essentially discuss it in the next class, and I will allow you to also like think through these details, right. We have discussed a lot of points, we will recap once again, right. So if you look at the Nyquist stability criteria, that is the Nyquist stability criteria finally. Of course, this is a criteria when g of s h of s does not have any poles and zeros on the imaginary axis. That is the case we started off with. If the open loop transfer function g of s h of s has k poles in the right of complex plane, and if limit s tending to infinity g of s h of s is either 0 or a non-zero constant, then for stability of the closed loop system, the locus of g of j omega h of j omega, as omega is varied from minus infinity to plus infinity, must encircle the minus 1 point k times in the counterclockwise direction. So essentially what we are saying is that we are saying p equals k, right, and then we want z to be 0. So what should be nc? It should be minus k, and that is k counterclockwise encirclements of the origin in the 1 plus g of s h of s plane, and that is going to be k and counterclockwise encirclements of the minus 1 point in the g of s h of s plane, and we are writing g of j omega h of j omega because like s is of the form j omega, okay. So that is why we are looking at this. Yeah, that case I will discuss what to do in the next class, right. So essentially that is the first case we are dealing with, right. Essentially what happens when no open loop pole or open loop 0 lies on the imaginary axis, that is the case we are still there. Now we will then see what happens if it does, what should be changed, right. So that is something which we will discuss.